So first, we will start with background of study. So for more than 2000 years, Euclidean geometry was the main system used to understand shapes and space. But its fifth postulate about parallel line was seen as more complicated than the rest. So because of that, mathematicians explored new ideas, and this led to the non-Euclidean geometries like hyperbolic, where many parallel lines exist, and elliptic, where there is none parallel. So even though non-Euclidean geometries are used in science today, most students still only learn about Euclidean geometry. So this can make it hard to understand newer ideas in physics or technology. So in this study, we will compare Euclidean, hyperbolic, and elliptic geometries and show how they relate to real-life fields like navigation and space science. Our objectives are to understand the Euclid fifth postulate and how it leads to a new types of geometry. So we explore the main feature of hyperbolic and elliptic geometry, compare all the three types based on the angle, line, and curvature, and relates them to real-world use like GPS and astronomy. So this also shows how changing just one rule can lead to a whole new system in mathematics. So basically, this study is important because it shows how geometry has evolved from simple, flat concept to more complex ideas used in science today. So it helps students to connect what they learn in class to modern topics like GPS, space science, and relativity. So it also encourages us to think more critically and see how just one changes in the rule can reshape the whole system in mathematics. So this study focused on the fundamental ideas in geometry, especially those related to Euclid's postulate and how triangle angles and curvature behave in different geometries. So we compare Euclidean, hyperbolic, and elliptic model clearly with some real-world context, but without going too deep into technical or advanced mathematical theories like tensor or calculus.
For historical background, Euclid's element written in Alexandria around 300 BC became one of the most influential works in mathematics. It collects all known Greek geometric knowledge into a single 13-book volume, a mathematical textbook that shaped centuries of study. What made element revolutionary was its structure. Unlike empirical methods, Euclid began with pure definition and logical build-up to complex theorem. This approach deeply influenced Western science and philosophy. The text was translated into Arabic during the Islamic era by scholars like Ibn al-Haytham and later into Latin in medieval Europe. During the Renaissance, Element was published in many European languages, in making classical geometry accessible to all. Later, René Descartes merged algebra with geometry, sparking analytic geometry. Sophie Germain later described this relationship perfectly. 2. Algebra is written geometry. Geometry is but drawn algebra. Euclidean geometry is built on 5 basis postulates taken to be true without proof. Postulate 1. A straight line can be drawn between any 2 points. This defines the idea of a straight line as a connection between 2 distinct locations. Postulate 2. A terminate line can be extended indefinitely. In other words, line segment can be stretched infinitely in both directions. Postulate 3. A circle can be drawn with any center and radius. This allows geometric construction using a compass. Postulate 4. All right angle are equal to one another. This defines the concept of angle and congruence, which is fundamental for comparing geometric figure. Postulate 5. If a line intersects 2 other lines and the sum of interior angle on one side is less than 2 right angles, the 2 lines will eventually meet on that side. This is the famous parallel postulate and the one that caused the most debate in history. The parallel postulate is the most complex and controversial of the 5. Unlike the others, it is not obvious and requires imagining of behavior of infinite line. Mathematicians spent over 2,000 years trying to prove it using the other 4 postulates, but all attempts failed. That's because it's independent. Its meaning, it can't be derived from the others. It eventually led to the creation of non-Euclidean geometries. In hyperbolic geometries, infinite line can pass through a single point without ever intersecting the original line. In elliptic geometry, no parallel lines exist at all. One simpler equivalent of Euclid postulate is Playfair's axiom, which is given a line and a point not on it, there is exactly one parallel line through the point. This axiom is easier to state and is used in modern geometry texts. The controversy around the fifth postulate transformed mathematics, in showing that multiple consistent geometry could exist, each with its own logic and assumption. The parallel postulate is the most complex and controversial of the 5. Unlike the others, it is not obvious and requires imagining of behavior of infinite line. Mathematicians spent over 2,000 years trying to prove it using the other 4 postulates, but all attempts failed. That's because it's independent. Its meaning, it can't be derived from the others. It eventually led to the creation of non-Euclidean geometries. In hyperbolic geometries, infinite line can pass through a single point without ever intersecting the original line. In elliptic geometry, no parallel lines exist at all. One simpler equivalent of Euclid postulate is play pairs exists, which is given a line and a point not on it. There is exactly one parallel line through the point. This axiom is easier to state and is used in modern geometry texts. The controversy around the fifth postulate transforms mathematics in showing that multiple consistent geometry could exist, each with its own logic and assumption.
Hyperbolic geometry. So what is hyperbolic geometry? So hyperbolic geometry is one of the two classical types of non-Euclidean geometry. So basically, hyperbolic geometry was developed independently by Carl Friedrich Gauss and with another two persons in the early 19th century. So it is a consistent and logical alternative to Euclidean geometry by modifying the Euclid fifth postulate known as the parallel postulates. So instead of only one parallel line through a point, in hyperbolic geometry there are infinitely many lines through that point that do not intersect with the original given line. So because of this change, triangles in hyperbolic geometry have an angle sums of less than 180 degrees. Therefore, there will be no rectangles exist in this geometry because they simply cannot exist under its rules. So the space is the space is negatively curved like a saddle, and the lines seems to curve away from each other. So lastly, this model of space is used in the theory of special relativity and complex analysis. So now, next let us look at the elliptic geometry. So elliptic geometry is also known as a spherical geometry. So it is a branch of non-Euclidean geometry as well, aside from hyperbolic geometry. So in this geometry, it would usually describe the shapes, distance on a curved surfaces, especially the spheres. So in this geometry, it is different from both Euclidean and hyperbolic geometry systems. Because in contrast to Euclidean geometry, which assumes a flat surface and allows the existence of parallel lines. So in this geometry, there is no parallel lines exist at all, as the line will eventually intersect with each other. So this causes the sum of angles in the triangle to be greater than 180 degrees. So next, just like in hyperbolic geometry, rectangle do not exist here because the space is positively curved like the surface of a sphere. So lastly, in this geometry also, the lines appears to curve toward each other, and technically there are no actual straight lines while only arcs existed. So this type of geometry is used in general relativity and is also important in navigation, especially over the curved surface of the Earth.
To better understand how different geometries behave, we can compare Euclidean geometry with its two main non-Euclidean geometry, which is hyperbolic and elliptic geometry, which each has unique characteristics that affect how we understand space, shapes, and measurement. So this table provides a side-by-side comparison across key properties. So for the first property is axiom. Euclidean geometry is based on 5 postulates by Euclidean, and the fifth postulate or the parallel postulate defines how parallel lines behave. In hyperbolic geometry, this postulate is modified to allow many parallel through a point, while in elliptic geometry, no parallel can exist. Second property is triangle angle sum. In Euclidean geometry, the interior angle of a triangle always sum to 180 degrees. Hyperbolic triangle have a sum less than 180 degrees, while elliptic triangle exceed 180 degrees. This angle variation is directly related to the curvature of the space. So for the third property is parallel line. On a flat Euclidean plane, there is only one line parallel to a given line through a point. Hyperbolic space allow infinitely many, while elliptic geometry being curved like a sphere has non-parallel. Next property is curvature. Euclidean geometry is flat with zero curvature. Hyperbolic geometry has negative curvature, often modeled like a saddle surface. Elliptic geometry has positive curvature similar to a globe. Next, line definition. In Euclidean geometry, lines are straight. In hyperbolic geometry, lines may appear curved depending on the model used. In elliptic geometry, straight lines are represented by grid circle like equator. And lastly is real-life application. We use Euclidean geometry in daily life building like structure or reading maps. Hyperbolic geometry is applied in relativity and network theory. Elliptic geometry helps in navigation, astronomy, and GPS system, where space curvature must be considered. In summary, to understanding these three geometries allow us to explore both the flat and curved nature of space, while Euclidean geometry form the foundation of classical geometry. Hyperbolic and elliptic geometry expand our understanding in the universe of mathematics, science, and beyond.
For the discussion part, we have real-world application and its diagram of geometry. Starting with Euclidean geometry. In architecture and construction, it helps design building using angle, symmetry, and parallel line for structural stability. Next, CAD software uses Euclidean principle to model objects in 2D and 3D for engineering and manufacturing. Then, surveyors use Euclidean formula to measure land area and define property boundaries through triangulation. Lastly, in robotics, Euclidean transformation like rotation and translation help robots move precisely. Then, this is a diagram standard plane of Euclidean geometry. This diagram depicts a simple construction in Euclidean geometry, specifically illustrating a proposition in involving circle and line segment. Euclidean geometry is based on flat two-dimensional space where lines are straight and parallel line never intersects. Next, hyperbolic geometry. It models complex network like the internet, where central hubs connect many nodes, while peripheral nodes are sparsely connected. Second, in data science, hyperbolic embedding improves link prediction in social network and recommendation system. Next, some cosmological models suggest the universe may have a hyperbolic structure under certain inflation theories. Lastly, artists like M.C. Escher use hyperbolic geometry in works like the Circle Limit series. Then, this is a diagram of hyperbolic geometry, which is the point K-disk. This is a two-dimensional model of hyperbolic space, where the entire infinite hyperbolic plane is mapped onto the interior of a finite circle. This model helps visualize the unique properties of hyperbolic geometry, such as the divergence of parallel lines. Finally, elliptic geometry. In navigation, airplanes and ships follow great circle routes, which are straight lines in elliptic terms. Second, GPS satellites rely on elliptic geometry to calculate position accurately by accounting the Earth's curvature. Next, in astronomy, the celestial sphere use great circles like the equator and ecliptic to track stars and planets. Lastly, geodesy measures Earth's size and shape over large distance using elliptic principle. So here is the diagram that illustrates the spherical triangle on the surface of a unit sphere, which is fundamental concept in elliptic geometry. In elliptic geometry, the space is curved like the surface of a sphere and lines are represented by great circles.
To conclude, this study helps us understand that changing just one rule in geometry, which are the parallel postulate, can lead to totally different types of geometry. Euclidean geometry is what we use for flat surface, like in buildings and land measurement. But for curved space, like the surface of the Earth or the shape of the universe, we need hyperbolic and elliptic geometries, which is non-Euclidean geometry. Each of these geometries has its own special properties and they are all useful in different fields. For example, Euclidean geometry is used in construction and design, hyperbolic geometry in internet networks and link predictions, and elliptic geometry in GPS and astronomy. This shows us that geometry is not just about shapes, but it's a powerful tool for understanding the world around us.